Thank you again. Okay, the next talk is going to be presented by Tajmale Afanja about towards biologically plausible and private gene expression data generation.
Thank you for the introduction. Hi, everyone. My name is Tajmale Afanja. I'm a doctoral researcher at CISPA, which is an Helmholtz Center for Information Security. Today, I present our work titled Towards Biologically Plausible and Private Gene Expression Data Generation. This is a joint work of CISPA and the German Center for Neurodegenerative Diseases. So our gene determine all sorts of things about us, as motivated also by the previous speaker, which also includes our predisposition to many diseases. So understanding our genomic information can help us better understand how changes in the cell happen, what causes them, how can it be prevented or manipulated. However, this vast amount of data is usually not easily accessible, which may be due to ethical, legal, or privacy concerns. And some work has even shown that anonymized data can sometimes be re-identified when combined with other data sources, as demonstrated by Homer et al. In 2008. So the question is that how can we make genomic data publicly and responsibly accessible? And so this will leverage synthetic data. So for our proposal, we define synthetic data as data that shares the same statistical property as the real data, and therefore can be used as a replacement for the real data. The promise of synthetic data is that none of the record in the synthetic sets can be re-identified or linked back to actual people in the real data. But several work has also shown that this is not usually the case, and sometimes synthetic data can learn too much from the real data and thereby compromise the information. To circumvent this, we go to differential privacy, which is a mathematically rigorous framework that allows the sharing of statistical information in database without compromising the user's information by protecting it. So let's say we have a database D with a person's information, and then we remove their data to create the D prime or D hat here. The differential privacy guarantees that an adversary, by just looking at this output from the randomized algorithm, cannot tell whether the user is in the data or not. And in order to upper bound this knowledge that the adversary can gain, or we use epsilon, in which the lower the epsilon, the higher the privacy protection offered. And in this equation, delta is the probability of the algorithm or mechanism rather breaking down. So our contribution in this work is that we provide the first comprehensive and systematic analysis of DP generation method that is applied to real-world gene expression data. We investigated 5 diverse private generative models, from simple density estimation methods to more complex deep generative models. And we evaluated these models on a holistic set of metrics targeting 3 principal axes, which are the downstream task utility, statistical property, and the biological plausibility. So the methods that we investigated can be broadly categorized into 2 based on how they do DP sanitization. So for example, we have the run-Gaius method, which transforms the data to low-dimensional space and add noise to the statistics, such as the mean and the Gaussian distribution that is used to learn this the Gaussian model. So, and while the private PGM and PrivSyn, they learn low-dimensional marginals and add noise to these marginals, whereby the synthetic data is generated. The other class of models, which are the deep generative models, there we apply DPSGD, which literally iteratively clip the gradient of the model to bound the sensitivity and also add noise to it. So Moving on, we considered different kinds of evaluation in order to holistically assess this model, because this is something that we found as gap in a previous work. So we considered statistical fidelity that looks at the marginal distribution statistics or joint distribution. We also considered how well the synthetic data can be used for a specific task. And in addition, we considered how well we can use the synthetic data for the domain-specific task, which we call the biological plausibility. So for the task utility, we train a machine learning classifier to predict the class, which is the disease in our case. And then we do the same for the synthetic data that is generated from the different models and compare the performance. While the statistical fidelity, we looked at the histogram intersection overlap score between the synthetic data and the real data across all of the columns and averaged this. While these two metrics are popular in literatures, we also included two different metrics that were inspired by our biological partners, which are the differential expression metric and the co-expression. For differential expression, we compare gene expression level between the real and synthetic data under different conditions. So this is the idea here is that genes are expressed based on different conditions, and if these conditions that are respected in the real data are also respected in the synthetic data, then we know that we've generated good synthetic data. So while co-expression looks at groups that perform the same function in the real data and try and ensure that it also exists in the synthetic data. So the data set that we consider for our work is the acute myeloid leukemia, which is a bulk RNA sequence transcriptome data set, where each row represents a biological specimen that is obtained from a patient, and each column indicates the average gene expression level from population of cells. And the task here is to predict 5 disease classes of leukemia. Moving on to results, for the task utility, we investigated different privacy budgets ranging from relatively high privacy regime, epsilon equals to 5, to low privacy regime, epsilon equals to 100. And we also do a comparison with a non-private model in which for pre-seen Ron-Giles and private PGM, it means we just set the noise value to 0. While for VAE and GAN, we train without the PhD. And we show here the real data reference to show us the upper bound of what is achievable. The takeaway from this machine learning utility is that most of the models can achieve relatively good utility, even at a high privacy, even at low privacy regime. What am I saying? Even at high privacy regime, which is epsilon equals to 5, while moving to like the histogram intersection metric that targets the marginal distribution, we find that for VA, for example, we're able to achieve a very high score, which is almost close to what is achievable in the real data. But as we move to the high privacy regime, we see a very huge gap, which signifies here that most of the data set that is generated here, it does not have high fidelity. And what is surprising here is that some of the models, such as the Ron-Giles and GAN, shows a negative result here, which we conjecture that this is probably due to they're not able to learn the distribution of the data very well due to the uniqueness of our data size. So the biological plausibility metric here shows here that in the non-private, some models are able to achieve very good DE gene expression by showing by their high score here. But as we move to the low to the high privacy regime, we find that this is generally not the case, and in fact, so private PGM here outperform the model shown in the non-private to be the highest performance. But this also shows a lot of false positive rates in which some of the expression value that is being shown to exist in the synthetic data does not exist in the real data. Well, the co-expression here, and the VAE has the best performance in non-DP setting, but in the DP setting, the co-expression values degrade and also shows a lot of false co-expression. This is probably much more visible looking at the GAN model and the Ron-Gauss model, where they don't they're not able to generate good co-expression, but they also give incorrect co-expression. So to summarize our work here, we looked at different metrics to better understand how well the synthetic gene expression data that are being generated. And we find that even though the machine learning task utility, which is mostly used in the machine learning world, are generally good for this privacy setting, but they break down when we move to domain-specific metric or like statistical metric. So which shows that we need a broad set of metrics to faithfully assess the generated private synthetic data. And we also need to develop better models that understand the domain that, such as like here we're looking at the gene expression data, and so that we can better make progress in that domain. And of course, we need bigger data sets because here we use a very small data sample. So thank you so much for listening. You can find our paper and code linked by scanning this QR code. I'm happy to take any questions. That was a rush.
Thank you so much. All right, thank you so much for staying on time. Any questions?
Thanks for the presentation. I have a question. Do you think that this new AI advanced model, like large language models, can address these challenges that you mentioned?
Okay. Which of the challenges, so that I can know how to answer your question? There are plenty of challenges.
Yeah, like the challenges that you mentioned are related to this deep learning model, like GAN and variational autoencoders and this, yeah.
So this is a good question because we have an ongoing work looking at large language model for synthetic data generation, applying DP. But I can say that it's non-trivial. It's very difficult to fine-tune, for example, LLM for this task. And but how we see this maybe potentially used is that if we can leverage the information, right, compressing these LLMs, but it also means that they have to encode this biological knowledge, which maybe because the data set is not readily available, maybe they don't have access to it. So it's like a chicken and egg problem, but we are still evaluating these models also, and they seem to have generally good performance, but I wouldn't say that they can solve the problem out of the box. I think we still need to look at the domain, redesign the models to fit into this domain that we care about, and this specific data set is quite challenging in its own way, and so yeah. I hope that answers your questions, but happy to talk about this a bit more because I have done research in that.
Great, thank you. I think we can take one more question if there's any. Okay, thank you very much for your talk.
Thank you for listening.